the two molecule, okay, and then yeah. So yeah, look at their relationship, okay. So if these two molecules are identical or yeah enantiomers, okay, so these two two protons should have same chemical shape, okay. So yeah, if they are constitutive isomer or kind of diastereomer, okay, so they will have kind of different chemical shape, okay. Yeah. All right, take a try, okay. So yeah, practice on yeah, just these three, okay, first, okay. And how many the proton signal you should see for these three molecule, okay. Right, remember, okay, so yeah, all C3, okay, C3, okay, so no matter yeah, yeah, what kind of environment, okay, so they will have same chemical shape, okay. So yeah, CH2, okay, depends, okay, so two protons on same carbon. So if there's no more yeah, chiral carbon, okay, so then they will have yeah, yeah, same chemical shape, okay. So yeah, if the two proton, okay, so yeah, if there's chiral carbons, okay, in the molecule, okay, then the the CH2 two proton will have different chemical shape because they are their topic, okay. Yeah, okay. So no, okay. All right, okay. So yeah, if you like, you can write your answer in the chat window, okay. Or kind of yeah, someone if you like, you can even turn yeah the indication, okay. So yeah, the yeah annotation, okay. So yeah, write down kind of yeah the yeah answer in the yeah yeah in screen, okay. So. All right, close, okay. All right, okay. So yeah, let me go through yeah all three one by one, okay. All right, the first one is actually kind of three. That's right answer, okay. So the T-butyl, okay. So all three kind of yeah, the methyl group have same chemical shape, okay. So that's one. No hydrogen here, no hydrogen here. That's quaternary carbon, okay. And then 2, 3, okay. So totally 3 signals, okay. All right, for the second one, okay. So much more tricky, okay. So there's a lot of symmetry, okay. So first, okay. So yeah, these two terminal methyl group same, okay. And then 2, 2, okay. These two are same. 3, 3, okay. All right, okay, and then eventually, okay, so yeah, for all four yeah protons, okay, all four protons, okay, on benzene they have same chemical shape, okay, so that's 4, 4, 4, 4, okay, because they are related by the symmetry plane, okay, also rotation axis, okay, so yeah, they have same chemical shape, okay. All right, so that's 3, 4, okay. All right, and the next one also yeah pretty tricky one, okay. So yeah, there are kind of yeah chiral centers here, okay, and then yeah the whole molecule is kind of yeah the yeah a chiral, okay, a whole molecule kind of chiral molecule, okay, and then break up symmetric, okay. So in this case here the yeah that's one. There's one hydrogen here, okay, 2, okay, 3, okay. So those three can easy to identify, okay, but here the yeah most important kind of yeah to these two hydrogen, okay. So CH2, okay. So CH2, yeah, already showed you here, okay. So if there's no chiral centers, okay, so the CH2, yeah, two hydrogen will have same chemical shape, okay. But if there's chiral center, these two won't be same, okay. So that's we call the enantiomer topic, okay. Called the DRC topic, okay. That's here the 4 and 5, okay. So this one you should see kind of 5 signals, okay. Yeah. Make sure you know how to do this kind of question, okay. So that's hard one, okay. But yeah. Eventually, okay, so after this chapter, okay, so if I give you one molecule, you should quickly identify how many procyclin, okay, you should say for this molecule, okay. Yeah. And this one we'll do the practice later, okay. All right, and then next topic is yeah, signal area, okay. So yeah, that's here also another information can be provided by a protonema, okay. So integration, okay. So yeah, quite often, yeah, if you see kind of your protonema, okay, so there kind of yeah, curve above each peak, okay, and then some kind of number underneath, okay. So yeah, and then this kind of number actually kind of yeah, indicate here area, okay, of this peak, okay, this signals, okay. So this area actually kind of proportional to relative numbers of protons, okay. So for example, okay, so we look at this is the two pending node, okay, two pending node, okay, so there's no symmetrical, so that's all the three kind of all four signal kind of show the four different kind of proton signal, okay. All right, okay, so for the integration of the individual signal, okay, actually kind of the proportional to the area, okay, so for A, 3 protons, say okay, A two protons, okay, and then B 3 protons, okay, and then C the 2 protons, okay, and D 3 protons, okay, and then we look at kind of their integration ratio, okay, so 23, okay, 27, 40, and then 28, and then 42, okay, relative ratio to the 2 to 3, 2 2, and then 2 3, okay. So nowadays kind of the instrument, okay, so can automatic kind of help you do the integration for individual peaks, okay, so that's modern spectrometer, okay, and so but occasionally you have to the little bit adjust, okay, get kind of more close kind of the signals, okay. All right, here's another example, okay. So this one, okay, so that's the t-butyl the acetate, okay, so ester, okay. So C3 okay, give one signal, and then t-butyl, okay, 9 protons on t-butyl group also give another signals, okay. So only 2 signals, okay. And then if you look at its the NMR spectrum, okay, so indeed 2, okay, so the C3 okay, 3 proton, and then t-butyl 9 proton, okay, relative ratio 1 to 3, okay, and then the integration for these 2 peaks, okay, so that's 23 to 67, okay, relative close to 1 to 3, okay, so just be keep in mind, okay, so the relative this integration, okay, so just show kind of relative ratios, okay, not kind of exactly kind of the number of protons, okay, so that's please keep in mind, okay. All right, okay, so from now on, okay, so if I give you one the structure, okay, not only you have to show me how many signals, okay, and then you can also tell me the relative ratio of each signals, okay, so integration ratios, okay. All right, so let's practice on this one, okay. All right, so first tell me kind of how many signal you should see for this molecule, okay, proton signal, okay, and then what's the relative ratios for them, okay. All right, if someone like here, you can also type your answer in the chat window or kind of tell on the annotation, okay. All right, so when you are working on this question, okay, so a couple of things, okay, so first we have quiz, okay, so this evening, okay, so quiz 8, quiz 5, okay, so cover IR chapter, okay, and I will turn it down from 8 until okay, so all right, also please write down your relative ratios, okay, I will turn out from 8 until 11, okay, so make sure bring your IR table, okay, so IR table on EdCat, okay, so you need this one for your the quiz, okay, and I'll also have actual office hour, okay, so from 2 to 3, just right after this class, okay, so if you need help, okay, please log back to your Zoom, okay, and also there's no class on Monday, okay, on Wednesday, sorry, okay, so both no class and also no lecture, okay, so no lab, okay, so just okay. All right, okay, so someone looks like it's erased it, okay. All right, so can anyone tell me how many signals I should see for this molecule, okay? All right, so someone said 2, any other answers? 3 is the right answer, 3 is the right answer, okay? There's 1 proton here, okay, don't forget it, okay, so so each carbon can have the 4 bonds, okay, so here only 1 bond, that means there's 1 hydrogen here, okay, 1 hydrogen, okay. Right, and then 2, 2, okay, so these 2 symmetrical to each other, okay, so there's kind of symmetry plane, rotating axis, okay, and then 3, 3. All right, okay, so now we can determine how many kind of the relative ratios, okay, for these 3, okay, so 1, 2, 3, that's the signals, okay. All right, so integrate ratio, okay, so normally people use this I, okay, indicate, okay, so only 1 protons, okay, and then 2 L kind of totally 4 protons, okay, and then 3 also 4, okay. So yeah, relative ratio for this 3 signal, okay, so would be 1 2 2 4, okay, 1 2 4 2 4, okay. So that's please keep in mind, okay. Right. So now you need to get another idea, okay. So the integration for all the protons, okay. So all right, okay. So now we move to the most difficult part of this chapter, okay. So that's the spin coupling, okay. So this morning the students something kind of get totally lost in this part, okay. So let me see. That's right, okay. 2 proton here, 2 proton here, okay. That's totally 4. Same thing for the 3, okay. All right, okay. So so 2 and 3 they have different chemical environment, okay. So remember, okay. So I said kind of the environment, okay. So they are not related by symmetry plane or kind of the kind of rotating axis, okay. Right. Another way to look at it, okay. So 2 is close to chlorine, okay. 3 is far away from chlorine, okay. They have different chemical environment, okay. So later we'll do some practice, okay. So don't worry, okay. So so just that's the word I like, chemical environment, okay. So whether they have kind of same kind of the proton or kind of same carbon or same kind of other subatomic group is stronger than one same molecule, okay. The same kind of the hydrogen, okay. Then they will have kind of same carbon shape, okay. So all right, okay. So now we move to the spin coupling, okay. So some of you maybe already noticed, okay. So for some proton signal, okay. So actually kind of split into small peaks, okay. For example, okay. So this is SO-acid kind of proton signal, okay. So we should see kind of 3 signals, okay, because there are C3, C2, okay, and then another C3, okay. So different colors, okay. And for the C3, okay. So the first one, the green one, okay. So that's just singlet, okay, 1 peak, okay. And then for the CH2, okay, so this red one, okay, you see kind of become the 4 peaks, okay, and then the relative ratio is kind of 1 2 3 2 1, okay, 1 2 3 2 3 to 1, okay, right. And then for this blue C3, okay, so 3 peaks, okay, and the relative ratio is kind of 1 to 2 to 1, okay, right. How that happened, okay, so that's the spin coupling, okay. So the hydrogen, okay, so itself can generate kind of very small kind of a micromagnetic field, okay, and then it's this micromagnetic field can have kind of influence to the neighboring hydrogen, okay. So just show what's happened, okay. All right. So if we look at these proton signals, okay, so this proton, okay, so can feel some kind of very micromagnetic field, okay, from the neighboring hydrogen, okay. So this is neighboring hydrogen, okay. So under external magnetic field, okay. So that's kind of external, okay. And then these protons, okay, so will kind of generate opposite the local magnetic field, okay. So one's opposite direction from external, one can same direction from external magnetic field, okay. And then this proton no longer feel kind of the only the external magnetic field, can also feel kind of this micromagnetic field from the neighboring hydrogen, okay. So right, so remember we just learned kind of the NMR kind of absorption frequency, okay. So equal to kind of H, okay, that's gamma, okay, and then 2 pi, okay, and then this beta extra, okay. All right, so if there's no other magnetic field, okay, so that's will be kind of same value, okay. But now you get kind of some actual one, okay, okay. So one is kind of H mu 1, okay, equals to H gamma 2 pi, okay, and then beta xt, okay, minus some kind of the opposite direction of the local magnetic field, okay. So we can call kind of the minus the H neighboring, okay. All right, so that's this one, okay, and then another one, okay, 2, okay, H gamma 2 pi, okay. So if the same direction, you get a reinforced kind of external magnetic field, okay. So that's beta neighboring, okay. Right, so that's here the I'll need to get higher. So in this case, yeah, original okay, only one signal, okay. So now you split into two, okay. So that's here the hold here, okay. So the neighboring the hydrogen magnet, okay. So split kind of here the these protons, okay. All right, just keep in mind, okay. So there are some kind of rules, okay. So in order to coupling, okay. So protons must have different chemical shapes, okay. So different chemical shapes, okay. So that's here. If they have same the chemical shapes, they won't couple each other, okay. For example, okay, the 3 hydrogen in methyl group, okay. So we know that kind of same chemical shape, okay. So in this case, they won't couple each other, okay. Although the kind of neighboring, okay, only 2 bonds away, okay. Yeah. All right, and then second kind of the 2 protons have become relatively close, okay. So then they can couple each other, okay. So 3 bonds away, okay. So within 3 bonds, okay, within 3 bonds, okay. So you can see here, okay. 1, 2, 3 bonds, okay. So then can couple, okay. So if you get more than 3, okay, for example, we have another proton here, okay. 1, 2, 3, 4, okay. Then that's no coupling between this green one and also this red one, okay. It has to be 3 bonds, okay. So that's please keep in mind. All right. Okay, so for the 2 bond away, okay, so we call the germinal coupling, okay. So that normally happen the 2 protons on the same carbon, okay. But normally speaking, kind of the CH2, okay, 2 protons, okay, have same chemical shape, okay. So then won't kind of couple each other, okay. But if there's kind of steric centers, okay, these 2 protons, okay, will be their stereotopic. They will have kind of different chemical shape, and then they will couple each other, okay. So that's something to keep in mind, okay. Not common, but we do see kind of germinal coupling, okay. Another kind of vaccino, the coupling case, that's most common coupling case, 3 bond case. So 2 hydrogen case couple each other case. So there are some kind of real chance kind of you can have long distance coupling case, but that's beyond all kind of lecture case. So we don't need worry about case. Just keep in mind case only the 3 or 2 bond case you can get kind of couple case. All right. So now we explain kind of why you have kind of 2 peaks, 3 peaks, and 4 peaks, 5 peaks, something. Okay. So that's kind of n+1 rule, okay, n+1 rule, okay. All right. So people find the following kind of interesting kind of rules, okay. So number of the neighboring hydrogen, okay, and then that's the signal split, okay. Or kind of how many peaks, okay. So 2 peaks, 3 peaks, 4 peaks, something, okay. So if there's kind of only no neighboring hydrogen, okay, so 0, okay. So that's shown here, okay. So this HA, okay. So it will be singlet, okay. So 1 peak, okay. Right. So if there are kind of 1 neighboring hydrogen, okay, so we still look at kind of this HA kind of signal, okay. So there are kind of 1 HB as it's kind of the 3 bond win signal, kind of neighboring, okay. So this is the number, and then the HA, okay, will become kind of the 2 peaks, okay. Right. So if there are kind of 2 neighboring hydrogen, okay, so 2 neighboring hydrogen, and then HA will split in kind of 3 signals, okay, 3 peaks, okay. And then if there are kind of 3 neighboring hydrogen, okay, and then HA will split into kind of 4 peaks, okay. And you can go ahead kind of this trend, okay. All right. So if we think kind of the number of the neighboring hydrogen as n, okay, and then you find kind of split signal equals kind of n+1. Right. So that's easy to kind of figure out, okay. So that's kind of n+1 rule, okay. So 1 hydrogen kind of couple with n equivalent kind of neighboring hydrogen, okay, you split into n+1 rule, okay. So that's the help you kind of identify, okay. So and very, very important kind of the rules, okay, help you kind of figure out how many kind of neighboring hydrogen, okay. So what's that mean, okay? So if you see a signal kind of split into X peaks, okay, so that's indicated it's the proton has the X-1 hydrogens, okay. For example, okay, so we see kind of 4 peaks, okay, 4 peaks, okay, we call it kind of quartet, okay, for 1 signal, okay. So we know that, okay, for this hydrogen, okay, are kind of the 3 neighboring hydrogen, okay. So that's pretty interesting, very important kind of the rules, okay, help kind of figure out the whole structures, okay. Right. Here comes kind of yeah, how do we see kind of doublet kind of 2 peaks, okay? So why we can see that, okay, right? So we use this HB as example, okay? So here's kind of HB, okay? So HB, okay, so yeah, if there's no neighboring hydrogen, you should kind of one signal here, okay? So yeah, so but here there's the one neighboring hydrogen, okay? So yeah, HA, okay, it's kind of 3 bond away from this 2 HB protons, okay? So this HA, okay, so yeah, generate some kind of the local magnetic field, okay? So one kind of same direction as local magnetic field, another kind of opposite from kind of the local magnetic field, okay? And then they will split kind of HB signals, okay? So yeah, because the intensity of this the 2 local magnetic field kind of same, okay? So in this case, you get kind of 1-to-1 ratio of the HB signals, okay? Yeah, so one kind of a little bit downfield, one kind of a little bit upfield, okay? Right, and then similar thing kind of here for the HA signal, okay? So yeah, we still use same molecule as example, okay? So for HA, okay, it still has 2 neighboring hydrogen, okay? So 2 HB, okay? And then under the external magnetic field, okay, so yeah, the combination of the local magnetic field from these 2 HB, okay, we will have totally 3 possibility, okay. So one these 2 HB, okay, have same as the local magnetic field as kind of external magnetic field, okay. Another one, okay, so the one kind of same direction, one kind of opposite, okay, so yeah. And third one, okay, so that's both have kind of opposite directions, opposite kind of the external magnetic field, opposite kind of direction from the external magnetic field, okay. So the total population for this 3 situation kind of 1 to 2 to 1, okay. So that's why for the triplet, okay, so you get kind of the signal kind of intensity 1 to 2 to 1, okay. All right. So that's the real the NMR spectrum for this this 112 trimethyl ethene, okay. Right. So for the A, okay, so yeah, you get kind of the triplet, okay, because there are 2 neighboring hydrogen. For B, okay, so yeah, this B, okay, get here the doublet, okay, because only 1 neighboring hydrogen, okay. Right. How about the quartet, okay? So quartet happened there are 3 neighboring hydrogen, okay. So yeah, we still use HA as example, okay, HA, okay, here, okay, and then yeah, HA has kind of the 3 neighboring hydrogen, okay, so HX, okay. Right, so yeah, for these 3 neighboring hydrogen, okay, so the 4 possibility, okay. So all these 3 neighboring hydrogen have same local magnetic field as the external magnetic field, okay. And then second kind of 2 same direction and then 1 opposite, okay. Third one kind of 2 opposite, 1 same direction. Last one kind of all 3 are in opposite directions, okay. And then all the population, all the kind of possibility called kind of the combination of the local magnetic field directions, okay, give kind of 1 2 3 2 3 2 1 ratios, okay. So that's why for the HA, okay, so you get kind of the quartet, okay, and then the peak intensity kind of 1 2 3 2 3 2 1, okay. Right, here's kind of a real example 1,1-dichloroethene, okay. All right, so yeah, we look at kind of the middle CH, okay, so that's HA, okay, and then 3 neighboring hydrogen, okay, and then that's Y cut kind of cortex, okay, intensity kind of 1 2 3 2 3 2 1, okay. And then if you look at kind of the HX, okay, so that's here the methyl group, okay. It's a methyl group, okay, only has the 1 neighboring hydrogen, okay, so yeah, N+1 rule, okay, that's doublet, okay. All right, okay. And here's kind of what looks like, okay, so yeah, for the different kind of split pattern, okay, so yeah, the singlet just 1 peak, okay, doublet kind of 2 peaks, okay, so yeah, and then people use D to indicate the doublet, D, okay, so the abbreviation for doublet kind of people just use the D, okay, it's not good D, okay, but it's fine, okay, and triplet, okay, so yeah, people use T, okay, indicate, okay. And then quartet, okay, 4 peaks, okay, so people use Q, okay. All right, and then 5 peak quintet, just kind of abbreviation kind of QUIN, okay. And then 6 peak sextet, okay, SEX, okay, abbreviation, okay. And then 7 peak, okay, septet, okay, code, okay. And then SEPT, okay. All right. Okay, and then relative ratio of the peak intensity. Okay, so that's actually you don't need to memorize. Okay, so just look at kind of the people draw this the Pascal the triangle. Okay, so if you cannot remember the ratios, okay, just think about kind of what's the shoulder two kind of the numbers. Okay, the sum of these two number. Okay, add together you get kind of this number. Okay, so for example, okay, so for the we do kind of the quartet. Okay. So the two shoulder number. Okay, so 1 and 0. Okay, so that's add together get 1. Okay, and then 3. Okay, so the two shoulder number. Okay, 1 plus 2 get 3. Okay, and for example, okay, this kind of success. Okay, so the 10. Okay, you 4 plus the 6. Okay, that's give 10, and then 5. Okay, so 1 plus 4. Okay, it's get 3 5. Okay, just the two shoulder number you add them together. Okay, just get kind of the ratios. Okay, so that's the easy to understand. Okay. All right, okay. So some rules of the split kind of the coupling. Okay, the first, okay, we already learned kind of the equivalent kind of proton don't split each other's. Okay, right. So okay, we one example. Okay, get a new page. All right. For example, this molecule. Okay, so the 1,2 dichromate ethene. Okay, so totally 4 protons. Okay. But these 4 protons all show same chemical shape. Okay, because they are the kind of rotation axis, simply plane. Okay, so they have same chemical environment, same chemical environment. Okay, one signal. Okay, so in this case here even they kind of the 3 bond way. Okay, 1, 2, 3. Okay, but they won't couple each other. Okay, so for this molecule, you should only see one signal. Okay, singlet. Right. Okay. But on the other hand, okay, so if they have kind of the different chemical shape, okay, then they will show kind of the couplings. Okay, so give me one example. Okay, so we use fluorine, hydrogen, and chlorine. Okay, so now we should see 2 signals. Okay, because of this H2 close to fluorine, this H2 close to chlorine. Okay, so they have kind of the different chemical shape. Okay, and then they will couple each other. Okay, so non-equivalent kind of proton will couple. Okay, so in this case for this molecule. Okay, so we pretty much see this kind of signal. Okay, because each proton has the 2 neighboring hydrogen, 2 neighboring hydrogen. Okay, so you get kind of triplet. Okay, n plus 2. Okay, so 1 plus 2. Okay. Yeah, so the RT NMR spectrum should see for this one. Okay, so we see kind of difference. Okay, because of the not only different chemical shape, you also split each other. Okay, so right. Second kind of the proton bond on the same carbon. Okay, CH2. Okay, so normally speaking, they won't kind of couple each other. Okay, so like this CH2, this CH2, this CH2, because they have same chemical shape. Okay. But okay, so if they have different chemical shape, okay, they will couple each other. Okay, so that's we call the germinal coupling. Okay, so that's a 2 bond coupling. Okay, so just 2 bond. Okay, so example show there for this molecule. Okay, we look at only HE and HD. Okay, so for HE, HD. Okay, so they have different chemical environment. Okay, they will have kind of different chemical shape. Okay, so all that. Okay, so because the HE. Okay, cis2 methyl trans to the alkene. Okay, HD. Okay, cis2 alkene. Okay, and then trans to methyl. Okay, so they have different chemical environment. Okay, different chemical shapes. Okay, different chemical shapes. They will couple each other. Okay. So because there's no other the proton in 3 bond way. Okay, so these 2 only couple each other. Okay, and then we look at kind of HD and HE signal. Okay, so both will be doublet. Okay, because there's the n plus 1 rule. Okay, only 1 neighboring hydrogen, and then 2. Okay, so that's a little bit keep in mind. Okay, so CH2. Okay, same chemical shape won't couple each other. Okay, so different chemical shapes. Okay, they will couple each other. Okay. Right, and then that's actually kind of the not common one. Okay, most common kind of the coupling is just 3 bond way. Okay, so 1, 2, 3. Okay, that's we call the vicinal coupling case. So long coupling range kind of possible. Okay, 3 bond. Okay, more than 3 bond. Okay, so 4 bond, even 5 bond. Okay, and those actually not covered in this class. Okay, don't worry about. Okay, so so for this class you only worry about kind of 3 or 2 bond couple. Okay, and then OH, NH will want kind of the couple with other CH, okay. So even in 3-bond way, okay. So example showed here, okay, this is the ethyl amine, okay. So we should see kind of 3 signal, okay, NH, and then CH2, C3, okay, shown here. C3, okay, so only this CH2 as kind of neighboring hydrogen, 2 + 1, 3, okay, so let's give kind of triplet, okay. And then interesting for kind of CH2, okay, middle, okay. So looks like it should be kind of totally 5 neighboring hydrogen, okay, but the NH, okay, so because quick exchange, okay, won't involve coupling, okay. And then in this case here, the CH2, middle CH2, okay, only can sense kind of C3, okay. So that here the 3 + 1, that's here give kind of quartet, okay. So 4 peaks, okay. And then also the NH protons okay, cannot sense CH proton, okay. So that's here normally NH only singlet, okay, 1 peak, okay. So in the world, okay. So just here don't count NH OH for the kind of coupling. N + 1 don't apply to NH OH. Right. So next kind of show you some kind of most common split pattern for certain functional group. Okay, the first one is the ethyl group. Okay, so ethyl group. Okay, so CH2, C3. Okay. Okay. Right. Okay. So for the CH2 case, so there are totally the 3 neighboring hydrogen case, so 1, 2, 3, okay, so 3 bond away, okay. So that's here the why the CH2 case you should see quartet, okay, we use QK label it, okay. Same thing for both, okay. And then for C3 case, so the only 2 neighboring hydrogen, 2 neighboring hydrogen, okay. So that's here the 2 + 1 triplet, okay. So in this case here for the ethyl group, okay, so you should see kind of the one quartet at higher chemical shape and then 1 triplet at kind of lower chemical shape, okay. And the integration ratio for this 2 peak case should be kind of 2 to 3, okay. So if you see this kind of the peak part, okay, so 80% that will be ethyl group, okay. That's please keep in mind, okay. That's the example for the ethyl benzene, okay. So you see kind of the ethyl peak. Right, another one kind of the isopropyl, okay. So isopropyl, okay, so we drew it here. So that's isopropyl group, okay. So here this carbon bond to something else, okay. Okay, and then for the this hydrogen, okay. So this hydrogen, okay. So you can see totally the 6 proton as its neighboring hydrogen, okay. So 3 here, okay. So that means here the for this proton, okay. So you should kind of the 7 peak septet, okay. Right. And then for this CH here the 3, okay. So the this 2, okay. So each couple only 1 protons, okay. So 3 bond, okay. 1, 2, 3, okay. So that means both will be doublet, okay. D, okay. Right. So in this case here the if you see some kind of high chemical shift case, so it's 7 peaks, okay, septet, okay. And lower chemical shift kind of the doublet 2 peaks, okay. And the relative ratio is kind of 1 to 6, okay. So 1 here and 6 here, okay. Then that means here the 99%, okay. So that's kind of isopropyl group in this molecule, okay. So that's here, please remember this here the coupling part, okay. Right. Okay, so by analyzing the split car pattern, okay, so you can help you figure out the whole structure of molecule, okay, and then by kind of determine number of the equivalent of the protons, okay, from kind of agent carbons, okay. To give you one example here, okay. Right. So this is the one molecule kind of proton in mass, okay. So there kind of the 2 proton for the triplet, okay, A, okay, and then sextet kind of the also 2 proton, and then that's B, okay. And then there kind of the C is the triplet and 3 protons, okay. Okay, so now how do we figure out kind of the structure, okay? So we kind of start kind of learn how to interpret kind of proton number, okay. Right, so we from kind of HC camp start from HC, okay. Right, HC, okay, so 3 protons, okay. Looks like here C3, okay. Right, C3, okay. So you see kind of here the triplet, okay? Triplet means kind of here the two proton NMR, two proton as kind of neighboring hydrogen, okay? Two proton neighboring hydrogen, okay? N plus one rule, okay? 2 plus 1, okay? 3 is triplet, okay? So that means here they say 3, okay? So C3, okay? So probably bound to kind of CH2, okay? So that's 2 proton, okay? And then similar thing, okay? So we look at HA, okay? So HA is also triplet, okay? So that means kind of HA is kind of 2 proton, okay? So very likely kind of CH2, okay? So CH2, the triplet means kind of another CH2 bound to it, okay? Okay, in that case, we look at the HB, okay? So HB 2 protons, CH2, okay? Right, and then that's kind of 5 protons, okay? So that's can give you the sextet, okay? So 6 peaks, okay? So that's means kind of say there's no CH5, okay? So very likely, okay, should be kind of 1 C3, okay, plus 1 CH2, okay? So that's give kind of totally 5 neighboring hydrogen, okay? So give kind of 6 peak, okay? Right, and then now we can piece them together, okay? So we know that HC, C3, okay, there's a neighboring hydrogen, H2, okay? Right, and then for HA, okay, so also H2 as neighboring hydrogen, okay, so that's C and that's A, okay, so that's no problem, okay, that's right, okay, so this is kind of triplet, it's triplet, okay, and then the middle CH2 actually kind of HB, okay, so totally the 5 neighboring hydrogen, okay, and then give you kind of the sextet, okay. Okay, so that's how do you use the NMR spectrum kind of figure out the carbon framework, okay, so whole carbon chain, okay. And actually this is the propyl bromide kind of NMR spectrum, okay, so that's also show you kind of propyl group kind of the NMR kind of patterns, okay. All right, okay, so now it's you guys' turn, okay. So we have 3 molecule, okay, so try to already label kind of what kind of signal you can see for for example first one ABC 3 signal kind of second one kind of only 2 signal AB, okay, and then third one ACB, okay. Right, so now you guys work kind of try to answer what kind of split pattern for individual signal, okay. So that's singlet, doublet, triplet, okay, or kind of quartet, whatever, okay. And if you cannot remember what's name code for the different split pattern, okay, so it's kind of write down 1 peak, 2 peak, 3 peak, 4 peak, 5 peak, something like this. Yeah. Right. So n plus 1 rule, okay, n plus 1 rule, okay. So if someone like, okay, so you can write your answer in the chat window, or just directly label on the screen using the annotation kind of the function, okay. Yeah, from now on, okay, so if I give you 1 molecule, okay, so not only you need to tell me how many kind of pro-signal you should see, okay, and then you have also tell me kind of integration ratio for individual, for all the protons, and also a split pattern for each peaks, okay, so doublet, triplet, singlet, whatever, okay, so that's please keep in mind. Anyone know the answer, okay? So we do it one by one, okay? For the first molecule, okay, what split pattern for A? Singlet, doublet, triplet, quartet. That's right, okay. A should be singlet, okay. So I just here use S, okay. What split pattern for B and C? Okay, so if you can do together, okay, that's better, okay. Okay. Anyone has other answers? Okay. Right, we do it one by one, okay? Nothing. So you have to look at kind of yeah. So for A, there's no proton in no neighboring proton in 3 boundary, okay? Right, so we look at B, okay? So B, okay, so yeah. This is C3, okay? So B has 3 proton as neighboring hydrogen, okay? And then 3 plus 1, okay, so that's 4, okay? B should get the quartet, okay? Okay. Right, and then for C, okay, so yeah. C has 2 neighboring hydrogen, okay? So that's only 2 from B, okay? So yeah, 2 plus 1, okay, that's the 3, okay? So that should be kind of, C should be triplet. Okay, B again, okay? Yeah, we do this way, okay? All right. So here's the B, okay? So B proton can sense the 3 protons, 3 neighboring hydrogen, okay? So yeah, I will do like this way, okay? That's B, okay? So 1, 2, 3, 3 bond away, okay? So yeah, in this case here, there are totally 3 proton, okay? So yeah, 1, 2, 3, and 1, 2, 3, okay? 3 proton, 3 bond away, okay? 3 plus 1, that's 4, okay? So 4, that's quartet, okay? Yeah, same thing for the C, okay? C also has 2 proton, okay? So yeah, 3 bond away, 1, 2, 3, okay? So that's here the 2 plus 1, a triplet, okay? So N plus 1 rule, okay? 3 bond away, okay? So yeah, let's show the okay. Okay. Only 3 bond. 1, 2, 3, 1, 2, 3, 3 bond, okay? So that's consensus, okay? So if you have more than 3 bond, okay? So yeah, yeah. 1, 2, 3, 4, 4 bond away, okay? So yeah, this one cannot sense this proton, okay? 3 bond, okay? Yeah. All right, got it, okay? So only 2 or 3 bond away, okay? So then you can count it, okay? So proton. More than 2, okay? Cannot do it, okay? Yeah, easily confusing, okay? Right, so how about kind of the second one, okay? Second one only has the 2 signal, okay? A and B, okay? How many signal we should see for how many peaks we should for A, how many we should see for B, okay? Anyone? The proton on the left, okay, so yeah, the too far away, okay? So more than 4 bond, okay? 1, 2, 3, 4, okay? More than 3 bond, okay? Don't count it, okay? Okay. Yeah, that's right, okay? So A should be quartet, okay? Because 3 hydrogen as neighboring hydrogen, okay? B should be triplet, okay? So no sextet, okay? So because only 2 hydrogen, okay? So here and here, okay? So yeah, 2 hydrogen, okay? So 2 hydrogen, okay? Neighboring hydrogen, okay? So yeah, no sextet, okay? So yeah, triplet, quartet, okay? All right, so now we move to a little bit harder one, okay? So yeah, just here, please here write down in the chat window, okay? What split pattern we should see for A, C, and B, okay? Yeah, make sure when you count protons, okay? So yeah, 3 bond, okay? 3 bond, okay? So yeah, if more than 3 bond, just ignore, okay? There's 1 couple, okay? So too far away, okay? Yeah, that's right, okay? A singlet, okay? Because yeah, singlet I label here, okay? No hydrogen, okay? In 3 bond away, okay? And then B, C, okay. Okay. Let's do B first, okay? B first, okay? So B only has 1 proton 3 bond away, okay? This one, okay? Only 1 proton 3 bond away from these 3 protons, okay? So that's B should be doublet, okay? So yeah, doublet, okay? So D, okay? Right. And then for so same thing, okay? So yeah, this D also, this B also doublet, okay? All right, so yeah. So no one have me tell me kind of what's the split pattern for C, okay? Anyone can tell me what's C? That's right, okay, subtat, okay. So C, okay, has totally 6 hydrogens, okay, in 3 bond away, okay. So 1, 2, 3, 1, 2, 3, okay. 6 plus 1, okay, so that's 7, okay, so that's called subtat. All right, okay, so now you guys learn how to do splitting coupling, okay. So again, okay, count hydrogen, okay, numbers, okay. So in 3 bond, okay, so if it kind of and then plus 1, okay, that's cut kind of split part, okay. All right, pretty good, okay. All right, and then we talk a little bit about kind of coupling constant, okay. So coupling constant as kind of refers to the peak distance, okay, between kind of split peaks, okay. Yeah, with them kind of you have some quartet, okay, so you kind of this peak and this peak and this peak kind of the distance between the peak we call coupling constant, okay. And then quite often so when you read some kind of NMR the papers, okay, so some kind of professional publications, okay, so people write down kind of this NMR signal is the 2.5 kind of the ppm, okay, that's the Campbell shift, okay, and then if there kind of split pattern, okay, labeled as kind of for example the triplet T, okay, and then followed by J equals to maybe 1.4, okay, so that's the J is kind of the coupling constant, okay. So if so J value really depends kind of how strong of the 2 signal couple each others, okay, how strong, okay. So sometimes kind of maybe from 3.4 up to like maybe 4, 5, okay. So very big difference, okay. So how strong, okay. But if 2 proton couple each others, okay, and then their J value will be same, okay. So and for example, okay, so the HA will cover HB, okay. So HA is quartet, okay. Actually, HH kind of quartet, okay. HB is kind of triplet, okay. And then the J value, okay, so it will be same, okay. So the HA equals to HB, okay. We kind of split after the counter constant will be equal, okay. Right, and then because they have kind of the same constant, okay. So then they will have kind of just identify whether kind of neighboring to each other. So, okay, that's one way to do it, okay. And also this J coupling constant are independent of the strength of magnetic field, okay. So if you record try to record the NMR spectrum for one sample at a different NMR instrument, okay. So the J values are same, okay. So that just keep in mind, okay. And just because of the coupling constant for the racino coupling kind of usually same, okay. So that's we can apply N+1 rule, okay. So what's that mean, okay? Right, okay. So we look at kind of these proton signals, okay, and then there's 3 neighboring hydrogen, okay. 3 neighboring hydrogen have same kind of J coupling, okay. So J same, okay. Right, and then you can get kind of N+1 rule, okay. So we should get kind of the quartet for this signal, okay. So that's reinforced, okay. So you can get kind of 1/3 kind of same direction, 1/3 opposite direction, 2 another kind of 2 situation kind of the half 2 same direction and kind of the opposite directions, okay. So that's the okay. So if the J coupling different, okay, so that situation gets kind of more complicated, okay. So you cannot apply N+1 rule, okay. So that's one we'll talk about kind of in the class next time, okay. So the different coupling constant, okay. All right, here we done the class, okay. So any questions? Today we talk about some kind of difficult material, okay. So the J coupling, okay. So make sure a little bit study for it, okay. So otherwise not easy get kind of figure out what structure, okay. And then for the future class, okay, how do you kind of interpret the NMR spectrum, okay. So it'll be pretty hard, okay. So any questions?